Hello students, welcome back. Let's go to section 3. A fair warning before starting. This section will get really deep toward the end, so it may not be for everybody. But the first half is okay, so what do? To tell the truth, I haven't made my final decision yet, whether to make this entire section optional or just the latter half of it. At this moment, I'll just defer the decision and just cover it as usual. Okay. Here's a reminder on what we did in section 1. We began from a homogeneous linear ODE with constant coefficients, and then we took the Laplace transform and did some algebraic manipulation to get capital Y of S as R of S over Q of S. Here, Q is the characteristic polynomial. Now, we take the Laplace inversion, and what we have? We have the general solution. Because the Laplace transform and then the Laplace inversion are one-to-one, this equation has a unique solution, y of t, given by this, depending upon the initial condition, of course. Everything looks good, but here's a problem. How do you calculate this Laplace inversion? We needed the partial fraction decomposition. So here we go, we have this. Theoretically, we'll have this expression, but it doesn't really work, so let's make it work. How do we do that? Here's an example. Just an example, not the general proof. For example, if we have something like this, really complicated, we can factor the denominator in this kind of form, and then based upon that, we can decompose the fraction R of S over Q of S by partial fraction like this. Can we do it? Yes, we can, because this rational function is proper. The denominator is characteristic polynomial, so it has degree n. The numerator has at most n minus 1, so it's okay. There's no quotient. Actual quotient is 0, so I don't have anything extra, so just these partial fractions and nothing else. No problem in terms of theory. And then we can take the, the Laplace inversion, and we're going to get the general solution. All good. Where is the hole? It's right here. Can we always factor like this? Linear factor and quadratic irrational factor, which can be transformed into complete square plus square. Is there anything else? Always like this. That's a problem, as a matter of fact, because linear factors will become exponentials and quadratic irreducible will become exponential times sine cosine. And do we have anything else? Of course, there are other functions out there, but why do we always have these kind of forms and nothing else? That, of course, is because of this tab over here, and that's something we'll have to establish. An example will not be sufficient. We need a proof, and that's what we are headed. Okay, the existence of solution is okay. What we need is the computational process. Okay, that's the motivation, and let's go to a couple of preparations. Number 1, complex number system. Everybody knows the definition, right? Imaginary number, I squared equals -1 and x plus yi. Addition, subtraction, multiplication, division, conjugate and modulus. Everybody knows all that, okay. And here are some properties of conjugates that I'd like to remind. Double conjugation, simply changing the sign twice, so yeah. This too. Modulus of conjugate is equal to modulus of the original. Multiply the conjugate and original and you get modulus squared, and here's the proof. And then other things here. It does not matter whether I take the conjugation before or after addition, subtraction, multiplication, or division. The proofs are, things like these are rather tedious, but we did all these. If you're unsure, you can always go back to lesson 1a and review that. Conjugate of a real number itself. Just 0i versus minus 0i, That's about it. Next preparation, the fundamental theorem of algebra. A complex polynomial of degree n has exactly n zeros counting in all those multiplicities. Or equivalently speaking, any complex polynomial can be written like this, factored completely in linear factors. Here, S1, S2, S3, those need not be distinct. If we have same thing repeating all over, then we'll have multiple zeros. Or you can express it like this, with distinct S1, S2, S3 with multiplicities like these. And, multiplicities should add up to n. Okay, alright, that makes sense. Okay. The proof, we don't do proof here. I usually cover it in Math 4520, functions of a complex variable. Not here. It's way above our head. But we can use it. So any complex polynomial can be completely factored. And then if you want distinct zeros, then we'll use this form. The latter form is the one we're going to be using in this section. Okay, so much for the preparation, and then let's go to real polynomials. Here we go. If f of x is a real polynomial, that is, all the coefficients are real, and it has a complex zero, then its conjugate must be also a zero. So if s, which can be written in alpha plus beta I, is a zero, then alpha minus beta I is also a zero. That's basically what this problem is talking about. So what do we prove? F of s is equal to 0, then f of s bar is also 0. That's what we have to prove. Now, how do you prove this thing? Well, this is the definition, isn't it? That's the definition of fs bar. As a matter of fact, I wouldn't say it's definition. Plugging s bar into this definition, this is the definition, we're going to get this form. So by definition, we get that. And we may have to do some manipulation, and eventually I want to get 0 in the end. That's basically what we want as a proof. And then this highlighted part, that's the key. What kind of manipulation am I going to do in order to get what we want? So, ready? Ready for the proof? Okay, here we go. Oh, by the way, this proof shows up a lot in Introduction to Proof course. I haven't had that course here in this UNT Dallas, but let's see. No, I haven't had exactly the same course in Minnesota either. I ended up helping a number of students, but I ended up helping a lot of students about this problem in multiple semesters, and I've seen it even in exam as well. Anyway, here we go. Just by definition, plugging in s bar into the definition, we get the first line, and then we apply the properties of conjugate. S bar to the nth power, what do you mean by that? That is, take the conjugate first and then repeat the multiplication. Here, down here, repeat the multiplication first and then take the conjugate later. What did he say earlier? It does not matter whether we multiply first or multiply later, conjugate first or later. So they are the same. Same here, they're all the same. Next, the key step. Each coefficient is real, so a1 is equal to a1 bar, a0 is equal to a0 bar and so on. an minus 1 is equal to a minus 1 bar and so on. Conjugate of a real number is itself. Basically plus 0i versus minus 0i makes no difference. Okay, they're all real, and then they all have conjugates now, so let's put everything together. Basically, we can use this or that, whatever. It does not matter whether you take conjugates before addition or after addition. They're the same, so we can put all those together, and we take conjugate later, and we do addition first. Now, what is this one downstairs? That's exactly this. We have f of s. This one down here, this one downstairs, is f of s. And that's 0. So we have 0 bar, which is equal to 0. We got what we wanted. Basically using the properties of conjugate over and over again. Okay, we got through it one. And then here's the next step. Let's factor the real polynomials. A real polynomial can be factored completely by either linear or quadratic irreducible factors. Actually, we can do better than just quadratic irreducible. It'll turn out to be a complete square plus squared. Proof goes like this. Let's begin with a real polynomial, and then we can factor it completely in complex space. You see? All these coefficients are real here, but it may have complex zeros. So S1, S2, S3 all the way over there. Yes, you can do that. And then let's do some manipulation. If the first one is real 0, and we move on. If the second is also real, let's move on until you meet the first complex 0. Let's say the first complex 0 is sk. Then down the road, there must be its conjugate somewhere. Sk bar somewhere. So move it up. Because multiplication is commutative, you can change the order and then move it up. I'm talking about something like this. Here's an example. We have the first complex 0 here, and then down the road, there has to be its conjugate because of the previous theorem that we proved. Multiplication is commutative, so we change the order. So let's bring this one up here. And then we can just break those apart. Okay, here we go. Get these and then break those apart. You don't have to foil it yet. Here's a little bit more clever method. Take this z minus ak and then minus times plus or minus bki. And here, excuse me, this is poor choice of characters. AKs are bad. I already used A's over here, so let's take some other characters. Excuse me. Alpha. Let's take alpha and beta. Excuse me. Let me make these corrections here. Give me some time. Z minus alpha k and this thing squared Okay, did I correct everything here? Okay, I broke this train of logic a little bit, so let's begin from let's restart. Let's restart all the way from the beginning. I'm sorry. Okay, it was poor choice of character, excuse me. I already used a's over here in coefficient, and using the same a's over here, it was just bad decision on my part. Sorry about that. Okay, let's restart. Let's go all the way back to the original expression. We have a real polynomial. Now we'll have complete factorization all the way down to linear factors because of the fundamental theorem of algebra, which applies in complex number system. So here, S1, S2, S3, those are complex numbers. Real number is a part of complex numbers, so some of them may be real, some of them may be complex, some of them may have non-zero imaginary part. Okay, start from the S1. If it is real, then move on. Another real, move on. Another real, move on until you reach first essentially complex with non-zero imaginary. Let's say this is SK. Let's suppose you made it at kth. And kth may very well be the very first. And by the previous theorem, its conjugate is also a zero. So if I rearrange the multiplication, I can bring this factor from down the road into very next step. And here's an example. So reals move on, reals move on, and finally we met the first complex. And then down the road there must be its conjugate somewhere, as we proved in the previous theorem. So change the order of multiplication, bring up, and that's what I got. Alright, and then we are going to break these apart. So we got these, and then their conjugates, so alpha k plus beta ki versus alpha k minus beta ki, and then break those apart. So z minus alpha k minus plus or minus beta ki over here. Here, minus minus, so this is plus. So what did he end up with? These two are conjugate. This is a real part, and that's the imaginary part. This is the real part, that's the imaginary part. These are conjugates. So if you multiply two conjugates, what do you get? You get the modulus squared. So the result is complete square plus square. Not just quadratically irreducible, but we ended up with complete square plus square, as we would like to have in things like this here. We need complete square plus square. Okay, we completed it for all the real polynomials. And then let's use that to decompose by partial fraction. How do we do that? R of S over Q of S. If you do that in complex number field, then the denominator is just purely linear only. So you can decompose by partial fraction like this. First, going power 1, 2, 3 all the way up to m on, and then that's the last. And then by taking Laplace inversion for each, we're going to get t0 power, which is just 1 times exponential, all the way up to t to the m minus 1 power, like that. And repeat, repeat, repeat all those for each lambda values. For reals, it's going to be a little bit more complicated because we have linears and then quadratic irreducibles. There are many. And the reals, the same way. Quadratic irreducibles here, we have the linear polynomial upstairs, and down here we have 1 power, 2 power all the way over there. So basically what we have over here is complete square plus square again. And then if we take the Laplace inversion, what we get? All those t to the some power times exponential from linear, and t to the some power exponentials times sine cosine from the quadratic irreducibles. And that's it. We don't have anything else. And those kind of functions are enough to generate the general solution. So the general solution can be written as a linear combination of these kind of things, and that's why we call them the standard basis functions. We are going to talk about those bases and linear spaces and some linear algebra in a separate video.